We evaluate artificial intelligence through a bottleneck of anthropomorphic bias. We build machines capable of processing millions of calculations per second, only to measure their cognitive capacity by watching them fail to drop a wooden block into a square hole. This bias extends to our highest benchmarks. The Turing test demands a machine imitate a human in a text dialogue. It measures a system's capacity for deception, leaving its ability to actually solve novel, unprogrammed problems entirely untested. Reverse Turing tests, like CAPTCHAs, operate under the same limitation. They tell us whether an algorithm can perform narrow optical recognition on distorted text, offering zero insight into general reasoning. Traditional psychometrics, like IQ tests, are similarly useless for artificial systems. These exams assume a baseline of human cognitive development, biology, and shared cultural context that a machine simply does not possess.
Alan Turing himself proposed the imitation game as a philosophical thought experiment to bypass the ambiguous definition of the word think. He did not design it to serve as a rigorous mathematical standard for cognitive capacity. To accurately evaluate the capabilities of any system, whether it is biological, artificial, or extraterrestrial, we must abandon human benchmarks entirely. True general intelligence requires an objective mathematical framework. It requires a measurement of pure adaptation across diverse environments, completely isolated from human bias. The field of reinforcement learning offers a clean foundational premise. Intelligence is the ability of an agent to achieve goals across a wide range of environments. This formula illustrates researchers Shane Legg and Marcus Hutter's formal mathematical definition of universal intelligence. Looking at the right side of the equation, an agent, represented by pi, is evaluated on its expected cumulative reward, v, across all possible computable environments, mu. Treating all environments equally corrupts the measurement. We cannot give equal weight to an environment that outputs static noise and an environment governed by complex physical laws. We have to weight them by probability. To solve this, the equation applies algorithmic information theory to assign a strict probability to every single environment. This probability is driven by Kolmogorov complexity. Simply put, environments that require a shorter code to generate are mathematically assigned higher probabilities. They carry more weight in the final score. Occam's razor is baked directly into the math. The universe of testable environments in this equation is infinite, but it is perfectly weighted towards simplicity. In theory, this equation perfectly defines intelligence. In practice, it creates a massive engineering crisis. It contains three infinities that make it physically uncomputable on any machine. The first infinity lies within the probability function. Kolmogorov complexity itself is strictly uncomputable. Due to the halting problem in computer science, you can never mathematically prove that you have found the absolute shortest program for a given sequence. The algorithm would search forever. The second infinity is found in the summation symbol. It requires an agent to execute infinite interactions across an infinite number of environments. And the third problem emerges from the rewards. You cannot calculate infinite cumulative rewards over an infinite timeline without the score simply scaling to infinity. Legg and Hutter originally proposed a theoretical fix for the reward problem. They strictly bounded the total possible environmental rewards to a maximum of 1. Bounding rewards fails in application. It forces the environment to hand out vanishingly small rewards over time. This mathematically incentivizes an agent to become overly greedy, grabbing as much reward as possible in early cycles rather than engaging in long-term strategy. To extract a real, executable intelligence test from this theory, we have to systematically slice these mathematical infinities down to rigid, computable boundaries. The first major engineering solution requires replacing raw Kolmogorov complexity with time-bounded complexity. Time-bounded complexity calculates the difficulty of an environment by factoring in the maximum computational response time required to generate the next state. It puts a hard cap on the search. The second major engineering solution is finite sampling. It is physically impossible to test infinite environments. The equation is altered to limit the test to a finite set of environments, represented by the variable m, and a strict finite number of agent interactions. Because we are now operating within finite boundaries, we can completely abandon Legg and Hutter's flawed bounded reward limit of 1. We shift the math from calculating cumulative, lifelong rewards to calculating the average reward per interaction. By discarding the infinities, these substitutions yield an algorithm that will actually run on physical silicone without freezing. But bounding the time and sample size exposes a critical vulnerability. If we randomly sample environments, most of the selections will be completely useless for testing intelligence. Random algorithmic sampling frequently generates passive environments. A screen that outputs static noise, regardless of what the agent does, offers zero discriminative power. Random sampling also generates dead ends. An agent might make a single incorrect choice and find itself permanently locked out of changing its reward state, turning the rest of the test into wasted computation. This decision tree visualization demonstrates the first strict requirement for a usable sandbox: reward sensitivity. At any given state in the environment, the agent's actions must maintain the potential to influence future rewards. The second vital requirement is that the environments must be balanced. A balanced environment relies on strict symmetry. The potential rewards must range evenly from -1 to +1. The core mathematical test of a balanced environment is simple. An agent taking completely random actions must achieve an expected average reward of exactly 0. By forcing environments to be reward-sensitive and balanced, the test filters out statistical luck. Any positive score achieved is undeniable proof of learned adaptation. The equation is now computable. The environments are perfectly balanced, but the algorithm still ignores the final and perhaps the most crucial variable of all, the physical speed of the agent itself. General intelligence operates across vastly different timescales. Human cognition happens in seconds, evolutionary biology spans years, and machines execute in nanoseconds. Applying a fixed global time limit to this test breaks the measurement entirely. If the clock simply runs out, an incredibly dull machine making millions of rapid, random guesses could easily accumulate a higher score than a highly brilliant but slow-moving agent. A universal test cannot rely on a static stopwatch. The testing environment must dynamically adapt its own timeline to perfectly match the native processing frequency of the specific entity being tested. This dashboard models the final engineering solution, the anytime algorithm. It applies adaptive testing logic to algorithmic complexity. The test begins completely blind, offering simple environments at the shortest physical timescales. Complexity scales dynamically based on performance. If the agent succeeds, the test dials up the environment's complexity. If it fails, complexity scales down. The physical time allotted scales concurrently, expanding exponentially until it perfectly synchronizes with the agent's action frequency. Because of this constant dual-axis calibration, the test can be interrupted at literally any moment to yield a mathematically bounded, highly reliable intelligence score. We have transitioned from an elegant but impossible theory of infinite sums into a practical, time-bound, adapted algorithm capable of running on physical hardware. We no longer have to rely on subjective benchmarks that ask if a machine can effectively imitate a human being. We now have the mathematical architecture to ask a purely objective question: what is the true algorithmic capacity of this system to adapt?